So, is it bouncing? La, la, la. So I wanted to wrap up this discussion of homology today. I'll begin with a word of prayer. So, dear Father, we thank you for this day. I thank you for these students. Just ask you to just bless this class, Lord. In your name I pray. Amen. So let me set the stage here. Remember, we have talked about a oriented simplicial complex, K, right? And an oriented simplicial complex, K, we can define the boundary map, right? And so something like this, if we had, say, a set of 3 chains, and then 2 chains, and then 1 chains, 0 chains. Well, below 0 chains, there's nothing, so you got 0 here. And with the boundary map, it gives us a way to connect m chains to m minus 1 chains. So like this is the third boundary map. This is the second boundary map. This is the first boundary map. This is the 0th boundary map. Who is missing? Oh, that's right. That's understandable. I guess she can watch the video here. Yeah, top hat, fine. Bring that ugliness in here. 1, 3, 9, 9. There. So, as we've discussed, for the simplicial complex, you have simplices of different dimension, right? I mean, and then formal sums of those are called chains, M chains, right? And the boundary map takes you from various different, it takes you from M chains to M minus 1 chains. And then we defined cycles and boundaries, right? And we said that the mth homology group was equal to, of K, was equal to the quotient of the M cycles by M boundaries, where I defined this last time. But specifically, in terms of the definition of cycle and boundary, what we're looking at is the kernel of the mth boundary map mod the image of the m plus 1th boundary map. All right. So going back to the definition of cycle and boundary from last time, we can see that a cycle, it's a cycle, an M chain is a cycle if it's in the kernel of the M boundary and boundary map, and a boundary is a boundary if it's in the image of the m plus 1th one. What's that?
Okay, so yeah, so the partial 4, partial 3, partial 2, those are all different boundary maps.
Right.
Since any of them twice.
Right. They're all defined by that overarching formula I gave, but technically speaking, they're different maps because they have different domains and codomains. Okay, so now, but we know how to calculate the dimension. What's the dimension of the mth homology of K is called the Betti number. This is equal to what's called beta sub K. This is the Betti number. Now, Rentland claims it describes roughly, what's he say? His words, not mine. Come on. Where'd you go? On page 145, he says that the dimension of HMK is called the mth Betti number of K, as we shall see, beta m of k basically counts the number of m-dimensional holes of k. I'm not sure I understand that sentence when I actually try to pair it against the examples. But anyway, we're going to calculate the homology. I don't disagree that homology has something to do with there being holes in space. I'm just not sure. I don't understand how to quite understand that sentence with what we're about to calculate. I'll just say that, okay? But anyway, so this, how do we calculate the dimension of a quotient of vector spaces? Remember, it's the dimension of the superspace minus the dimension of the thing we're quotienting by, right? So it's just that. This is the dimension of the kernel of the mth boundary map minus the dimension of the image of the m plus 1th boundary map. So if we want to calculate the homology of the circle, all we have to do is find a triangulation of the circle and then calculate how these boundary maps work out as we look at the different kinds of m chains that are supported by that triangulation. So for a circle, we just look at this. I mean, if you take this triangle, and not the solid triangle, but just the edge, okay? Not the filled-in triangle, but this. You can see that you can deform that without tearing, right, to this. Right? You can just kind of think about blowing out the edges, so to speak. That's a homeomorphism from the triangle K to the circle, and so that means that that triangle is a triangulation of the circle. In particular, we'll label P0, oh man, remember the diagram. 50-50, right? P0, I'll say P0, P1, P2, hopefully I'm right, all right. Okay, so then, this is the thing that, we've talked about sort of heuristically, but now we need to get more specific. What do zero chains actually look like? What is the set of zero chains here? Things like C0, P0. Oh, sorry. Bad notation. A0, P0. Plus A1, P1 plus A2, P2. This is sort of a generic zero chain. So this would be what a generic zero chain looks like. A generic one chain has, what would a generic one chain look like? So it'd be something like B1, P0. Oh, let me make sure I don't mess up the notation. B0. B0, P1, P2, plus B1, P2, P0, plus B2, P0, P1. That is what a generic one chain would look like for the triangle. And that's it. See, there is no two cycle. There's no two chain here because it's not the solid triangle. It's just the edge. Okay? So like C0K is just equal to the zero space here. So in fact, in this construction, the zero chains, this is a three-dimensional space. The one chains also happens to be a three-dimensional space, and the zero chains, well, they're I meant two. This last one, the two chains, well, that's also zero-dimensional. So this notion of dimensionality, I mean, I'm I'm not thinking of these as a subspace of R2 or something, right? I'm looking at a vector space where the basis is the independent, the finally independent points, P0, P1, P2. In that sense, it's three-dimensional. It's not. All right? And there's no linear dependence amongst these one simplices, right? There's no way I could build any one of these line segments from the other. So we just think of those as a basis, and this is a three-dimensional space. Yeah.
How many dimensions did you say were 0?
Three-dimensional, because it's got those three independent points. Okay, so then now we have, all right, that's what's in front of us. Now we just need to calculate the boundary maps in each case and decide what their kernel and image is. So let's start out with, how about like the boundary 0, which maps from, C0 to 0. So the kernel of the zeroth boundary map is C0, right? Great. How about the what else could we say? I mean, that's all we really need, because this is for m equals to 0, 1, 2, and so forth. So like, I'm only interested in kernel of the zeroth boundary map and up. So the next thing I need to do, that's pretty much all I need to say about the zeroth boundary map. How about the first boundary map? What can we say about boundary 1? Well, boundary 1 would act on what? Let me call this thing, I need to give this a label so I don't have to write it all out again. Let's call this thing C1. All right, for generic 1 chain. So boundary 1 on C generic 1 chain is what? Boundary map on this is what? It's B0 times P2 minus P1 plus B1 times P0 minus P2 plus B2 times P1 minus P0. What is it? So I'm trying to understand what the mapping is by looking how it acts on a generic element. This is pretty standard linear algebra, right? You take a generic thing, look what happens to it. That helps us understand the linear transformation, which in this case is boundary 1 map. Okay, now what we do is just rewrite this formula a bit. So what we're looking at here is B1 minus B2 times P0 plus parentheses. Now I'll group the P1 terms together. I've got B2 minus B0 times P1. And finally, what do I got for my P2? I got B0 minus B1 times P2. So just to, here's what's going on. We have, we have C0, we have C1. C1 of K, the boundary map, boundary 1 maps to C0 of K. The basis, which I'll use B for here, big B. Big B1 basis is what? It's it's P1, P2, P2, P0, P0, P1. That's the basis for the 1 chains, right? And then C0 has basis, I'll say basis 0. The basis for the 0 chains is formed by P0, P1, P2. So if I look at the matrix of the boundary 1 map with respect to the, beta 1 going to B1 going to B0, base choice of basis, right? Then the matrix I can write down. By our usual linear algebra, right? So what's the, when we calculate the matrix of a linear transformation, first column is what? It should be boundary 1 acting on the first basis element, which is P1, P2. And then we calculate the B0 coordinate of that. Then we take the boundary 1 acting on P2, P0. We calculate the beta 0 coordinate of that. We take the boundary 1 acting on the third basis, which is P0, P1. We calculate the beta 0 B0 coordinate of that. So what is that? Let me just cheat a bit. Let me just look. This means that this means what? This means that up here, right? That B0 equals to what? B0 is 1, B1 and B2 are 0, right? For the first column, we have one copy of B0, we have 0 of these. Which then means, if I go into the formula we just worked out, we have what? B0, it just gives us this term right here, right? And so that means we're looking at the coordinate vector of what? P2 minus P1 with respect to the B0. And then we're looking at the coordinate vector of P2 minus P0 with respect to B0. We're looking at the coordinate vector of P1 minus P0 with respect to the basis for the 0 chains. But what are those? Because I told you the basis for the 0 chains was P0, P1, P2. So that makes this 0, minus 1, 1. This one, minus 1, 0 P1s, 1 P2s. And then finally, minus 1 P0s, 1 P1s, 0 P2s. Now, if you look at Rentland, this is not how he does it, right? He just says this, he basically just writes down a matrix equation and says that that's the matrix of the map. And he doesn't actually state the bases explicitly, but I just did because I wanted to make it clear what's going on in terms of linear algebra that you've probably forgotten. Or you're at least by now uncomfortable with, right? No? Questions? Yeah.
What was the second to last matrix?
This one?
The second to last.
These are the coordinate vectors in the beta 0, the B0 basis for these 0 chains. So for example, P1 minus P0 is equal to minus 1 times P0 plus 1 times P1 plus 0 times P2. And then we rip off the coefficients, minus 1, 1, wait a minute, third one, right? Minus 1, 1, and 0, that gives me.
Where are those things coming from? Those are coming from the C1K up there?
Where is what coming from? These?
Each of those.
That's partial boundary 1 acting on the basis for the 1 chains. the 1, 2 line segment, the 1, 2, 1 chain, the 2, 0, 1 chain, the 0, 1, 1 chain. These 3 1 chains form the basis for the 1 chains. The 3 independent legs to the triangle. Yes?
So, is there a change in sign for the middle one or something that I'm forgetting?
Oh, did I mess it up?
Because you said you have P1, P2, and you have P2, P0, but then you have P2 minus P1.
I had P2 0 here. Yeah?
Yeah, so why is it P2 minus P0 rather than P0 minus P2?
Oh, I had P0 minus P2 here, didn't I?
Yeah, it's in the main.
Oh, yeah, that's supposed to be P0 minus P2. That's just an error. Thank you. And so that would make this 1 and minus 1. Thank you. Okay, great. Yep.
Could you say like one more time how you got those coefficients in front, or like show like where they came from?
Which coefficients?
Like the ones in front, like the P1 minus P0. I'm just confused about where they came from.
These?
Yes.
Oh, I'm just saying minus P0 is minus 1 times P0. P1 is 1 times P1. And use your imagination, there's no P2 here, so it's 0 times P2.
Okay.
The reason I'm doing that is that the basis for 0 chains that I declared has the ordering P0, P1, P2. So I have to take an arbitrary 0 chain and look at it as a linear combination of the basis in that order in order to see what the coordinates are, namely these, for a given column.
So you're just basically just saying like there's not a P2 there, so then the other ones just follow with whatever signs they were with.
Right, right. The reason I'm saying this is the homework problem I give you guys, in order to make sense of it, you need to state a basis for each set of M chains for your object, right? Once you fix that basis, then you can understand what the matrix looks like and so forth. But, I mean, you could do the calculation like Rentlin has. You don't have to do it exactly like I'm doing it or anything like that. But, okay. Now, long story short, now that we've looked at boundary 1, you can tell me that the dimension of the image of boundary 1 equals to what? What's the dimension of the kernel of boundary 1 equal to? Remember, for a linear transformation, the dimension of the image is the rank of the matrix which represents it. This matrix, if you add the rows together, you get 0. Yet it clearly has 2 linearly independent rows or columns, right? This means that it has rank 2, right? The dimension of the image is 2. The dimension of the kernel is 1, right? Remember, rank nullity says that the dimension of the image plus the rank plus the nullity of the matrix has to be the number of columns, which is 3.
You said there's only 2 linearly independent columns?
At most 2. Pick any 2. Yeah. Okay. So now that we've done the work, we can look at let's see here. What's beta 0 equal to? The beta 0 of k will be, what is it? Its dimension of the kernel of the 0th boundary map minus the dimension of what? The image of the first boundary map, right? Which is what? We figured out the dimension of the kernel was, oh, well, I didn't say it, but what is it? If the kernel of the boundary map is C0, what's the dimension of the kernel? If it's all 0 chains, that's a 3. 3. So we have 3 minus 2, which is equal to 1. So the 0th Betti number for the circle is 1. Then next up, we could try to calculate the first Betti number. Beta 1 of k would be what? The dimension of the kernel of the one boundary map minus the dimension of the image of the second boundary map. What's boundary? What's boundary 2 look like, though? Let's think about that for a second. What is boundary 2 map in this context? It goes from the 2 chains of the triangle to the 1 chains of the triangle. But what is this equal to? Right, 0. Because the triangle's not filled in. It's just the edges. So that's just 0. So what's the image of 0? It's just 0 again, right? So the image of the 2 boundary map is just 0. Which means that beta 1 of k is nothing more than 1 minus 0. Which is also equal to 1. Now, if we look at like beta 2 of k, that would be equal to what? How's it go? The kernel of boundary 2 map mod what? The image of the third boundary map. But actually, the second boundary map, I mean, there are no, the thing is then C2k, C3k, C4k, all the higher C's, they're all just 0. So all of the homologies, of 2, I'm missing a dimension here, sorry. This is H2k, sorry. But this is just 0. Because Cm of k is equal to 0 for m equals to 2, 3, 4, et cetera, et cetera, et cetera. So in summary, what we have shown is that the mth homology of the circle is equal to 1 if m equals to 0 or 1, and it's 0 if m is greater than or equal to 2. Now technically, we just calculated the homology for the triangulation of the circle, but the theorem, which is outlined in Rentlen, is that that data is preserved. Like if you calculate the homology of the triangulation, you've also calculated the homology of the honest to goodness circle. All right? And the interesting thing is that this also has to do with other notions of topology. So like earlier in Rentlen, he describes what's called the Duram cohomology. So the Duram cohomology, it is likewise formed by a quotient. Or, homology, if you like. Don't worry about the difference in words at the moment. But there, you look at quotients of, I believe, closed versus exact forms. You look at these quotient spaces of closed differential forms versus exact forms. The closed forms are the ones that exterior differentiate to 0. Those are like cycles. The exact forms are differential forms who are the exterior derivative of another form of smaller degree, much like boundaries. And a deep theorem is that this Duram cohomology and the homology actually match up. They're both ways of calculating the same thing about the space. So non-trivial homology actually speaks to the existence of some differential form, which, when differentiated, gives you another one. In other words, this is some kind of really convoluted way of finding potential energy functions for vector fields. But anyway, that's just kind of a far-out comment in here. So I think I've done enough that you should be able to make sense of your homework problem now. So I will go on. Oh, I should mention, you might enjoy reading the next section on the, So he has one more example I didn't cover for the disk. All right, you can look at that. And section 5.3 is on the Euler characteristic, which is a really neat thing you can do with the Betti numbers. If you take the alternating sum of Betti numbers, it gives you the Euler characteristic. And the Euler characteristic is a rather well-known topological invariant. I mean, Euler. So it's a little bit old. And you might have seen it in high school or something. It's possible if you had a particularly good teacher. But it's a fun thing you can calculate for various shapes. He says the form you might have seen at high school is vertices minus edges plus two faces. You add those, take that alternating sum, and that gives you the Euler characteristic. I mean, he has some rattled off here, like the Euler characteristic of a point is 1, the Euler characteristic of a one simplex is 1, the Euler characteristic of the Euler characteristic of the circle would be 0, the Euler characteristic of the filled-in triangle is 1, and so forth. But anyway, you might find that interesting if you look at it. I'm going to move on, as we have to go on. So, what is up next? Well, we have now reached chapter 12 of Dummett and Foote. All right. So chapter 12.1, section 12.1, I should say, is on, quote unquote, the basic theory. All right. Now, part of the reason I covered this rather elaborate example of a R module, right? Well, there's different reasons. I wanted to see I wanted you to see that when we look at these, chains, like this is what we were talking about in the video I posted, right? The, exact and image and all that different stuff. That sort of sequence of modules actually has deep significance in terms of calculating things which are of interest, and I thought this might be an interesting example to at least see. So, now we've seen it. Oh, getting back to my comment. I just don't see how a circle has both a zero-dimensional and a one-dimensional hole. He says that the Betti number it roughly means that there's that size hole in the space. There's a zero-dimensional hole in the circle? I don't understand what that means. There's a one-dimensional hole in the circle? I don't know what that means. I misunderstand something. The circle is the one-dimensional hole. Yeah, I'm not sure what that sentence meant. Anyway. Anyway. I'll just tell you this, guys. Understanding what homology and cohomology means is, a deep and interesting problem that people are still working on. Just because you can calculate something doesn't actually mean maybe you have a visual understanding of it, and maybe you never will. That's the interesting thing, is we can calculate things with algebra even when we can't intuitively understand them. All right. I hope you panned over, right?
Yes, I did.
Okay. Otherwise, I kill you. No, it's okay. Okay, so section 12.1. Definition. The left R module M is a Noetherian R module provided it satisfies the ascending chain condition on submodules. So what that means is that whenever we have M1 contains M2, contains M3, and so forth, if we have this increasing chain of submodules, then there exists some M in the natural numbers such that M sub k is equal to for all k greater than or equal to m. In other words, eventually, the sequence of submodules becomes constant, right? There's like a largest one it has to settle on. Likewise, the ring R is said to be Noetherian if it's Noetherian as a left module over itself. All right. Now, this Noetherian condition leads us to theorem 1. And theorem 1 says the following: are equivalent. Number 1, M is a Noetherian R module. Number 2, every non-empty set of submodules contains a maximal element under what? Under inclusion. And then 3, and this is the one that's kind of like, what? Every submodule of M is finitely generated. Now, this we talked about before, right? The notion of finitely generated. So this Noetherian condition is sometimes called a finiteness condition, right? Any one of these gives us this Noetherian R module, which the thing we're primarily interested in is that every submodule of M is finitely generated, right? There's a corollary to this. If R is a principal ideal domain, then every non-empty subset, every words, let me write it down, corollary 2, if R is a PID, what's that mean? What's that? I just didn't hear you. Principal ideal domain, we have a winner, yes. Then every non-empty set of ideals of R has a maximal element. I've butchered my sentence. If R is a PID, then every non-empty set of ideals R has a maximal element and what else? And R is a Noetherian ring. All right, so PID, in other words, in short, PID implies Noetherian. All right. If we have a ring which is a principal ideal domain, then it is Noetherian. All right. Proposition 3. What's Proposition 3 tell us? Prop 3. let R be an integral domain. All right? And M a free R module. A free R module of rank. I said my K became a G somehow when I was rank, not ring, rank N, which is not infinite. All right. Then any n plus 1 elements are linearly dependent. Meaning that for any y1, y2, yn plus 1 in M, there exist R1, R2, Rn plus 1 in R, not all 0, such that what? R1y1 plus R2y2 plus plus Rn plus 1 yn plus 1 equal to 0. And he gives two proofs of this. All right. I haven't said anything about the proof of the theorem 1 or corollary 2 because I don't really have much to add there. You can read what's in Thumb and Foot. But here I think I can explain proposition 3. And it's kind of fun because it ties us back to last semester. All right. So what does this say? This says in some sense that free modules, right? A free R module, at least if R is an integral domain, it behaves like we're used to from linear algebra, right? I mean, what does it mean for it to be a free R module of rank M? What's this mean? I know it's been a little bit since we were talking about it, but you guys remember? This means that M is R module homomorphic to what? Rn, right? Do you know why we talk about Rn? It's because we're in nursing. It's hilarious, isn't it? Yeah. Okay. It's not my joke. I was trying to get out today, see how it goes. It's more relevant here. I tried it out in the map room. This is closer to, this is still not nursing technically, right? I mean, okay, anyway. So suppose we have an integral domain and, suppose you have these n plus 1 elements like this. What he said, his first argument is to pass to the field of fractions, right? So if we have an integral domain, we can construct the field of fractions, right? So if you construct the field of fractions, and then if you could find a non-trivial linear dependence in the field of fractions, right? Why would that give you a corresponding, I mean, every linear dependence in the field of fractions corresponds to, I mean, you can go back to a linear dependence in the underlying ring. By doing what? I mean, if these are all in the field of fractions, there are things of the form what? Like a1 over b1, y1, plus a2 over b2, y2, plus plus an plus 1 over bn plus 1, yn plus 1, right? So if I have a free R module and I can pass to the field of fractions, which then puts us essentially in Fn, right? And I know I can't have I can't have more than n linearly independent vectors in Fn, right? I mean, we know this from linear algebra. But anyway, essentially the point in his proof is that if you had such a linear dependence in the field of fractions, what could you do? He says you could clear out the denominators. What does he mean by that? He means just take this and just multiply by the product of all the denominators, and then that will give you a corresponding linear dependence in the ring itself, right? Well, in the R module, actually. So like A1 bar, Y1, AN plus 1 bar, YN plus 1 equal to 0, where here A1 bar is the horrible B2, B3, Bn plus 1 times A1, etc. The B1s cancel and everything else is left, right? It kind of reminds me of that proof of the Chinese remainder theorem we did once upon a time. But anyway, this is a result we have. If we have a free R module of rank n, then we can have at most, we can't have n plus 1 linearly independent. If we have n plus 1 elements, it has to be linearly dependent. All right. Now, fortunately, we started 5 minutes late, so I still got 5 minutes. Woohoo! Next up, we define the torsion. What's the torsion of M? Tor M is x in M such that what? Rx equals to 0 for some 0 not equal to R in the ring. It's the so-called torsion of the R module. Now, he does assume here that R is an integral domain, all right? And so that's the torsion. Oh, fine. I'll let you guys go. I mean, what I'm trying to get to here, I don't think I have time to even write it, but our main goal here in the near future is to get to theorem 5, all right? Theorem 5, the fundamental existence invariant factor form says that if we have a finitely generated R module, then, and what would a finitely generated R module be? Maybe one that meets the Noetherian condition, right? So if M meets the finiteness condition, then it's isomorphic to the ring R-fold times direct sum with R mod principal ideal generated by A1, direct sum with R mod principal ideal generated by A2, direct sum, direct sum R mod the principal ideal generated by AM, where A1 divides A2 divides divides AM. This is the so-called invariant factor form of the fundamental classification theorem of, existence theorem of finitely generated R modules. And so I'm not going to prove this for you because, well, I'm lazy. But what I want to do is to try to see if we can't understand this theorem with a couple of important examples. All right. The main examples we're looking at will be linear transformations and the fx module. All right. And then also just finitely generated abelian groups. So things like Zn cross, like Z4 cross Z5 cross Z6 and stuff like that. So this R to the R piece, the torsion of M is essentially this piece. So if it's torsionless, it turns out it means that this R to the R piece is gone. R is equal to the Betti number of M. That is not at odds with the use of Betti number that I just gave you in the example. The homology we looked at was an R module. What was the torsion piece? There was no torsion piece, right? It was just, there was just Rn as it happened. So like this wasn't even present, and we just had R. Anyway, we'd like to understand this. And interestingly, for a linear transformation, the fx module, this part's not even there. And it's all just about this. And these actually end up corresponding somehow to like the different blocks in the Jordan decomposition or something like, not quite that, but related to that. So I will hopefully explain that to you guys next week. So anyway, thanks. I shall shut up.